Greetings, everybody. Thanks for coming to my talk. I'm going to be talking about automated creation of shellcode under situations where you are restricted in the bytes and the encoding you're allowed to use. My talk is kind of long, so I'm just going to get right into it. So to get us all on the same page, to briefly recap how memory corruption exploitation works, you have some program that's executing, and then the program accepts input from the user. This is the point where we insert our malicious input. And then throughout the course of program execution, it's going to validate that the input matches some input specification and throw the inputs away if it doesn't. And then it may do some sort of transformation of the input along the way. And then continuing to execute, a vulnerability will be triggered by the input. And finally, this is going to cause our shellcode, our input, in other words, to execute. So throughout the course of input validation and transformation, certain constraints upon what bytes we're allowed to send for our shellcode might come into existence. So for example, if our input is passed to stir copy stops copying after the first null byte is reached, which means that our shellcode can't have any null bytes in it. Or for example, the input may be passed to a function that makes the string uppercase, in which case we can't have any lowercase characters in our shellcode. If input's ever used as a format string, we have to be careful about the % character. And then you might have other validation along the way of ensuring that the characters are printable, ensuring that they're alphanumeric, and so on. And so these are a couple of common cases that you may run into. But really, any individual vulnerability scenario may restrict the type of inputs you're allowed to send in any arbitrary way that I couldn't capture on one single slide. So the effects of restrictions like these are to limit the machine code bytes that we are allowed to send. So to be clear about it, this slide duplicates one of the opcode map tables from the Intel manuals. And I have highlighted in red those instructions that you are not allowed to use if your input is restricted to be lowercase alphanumeric. So as you can see, it's a pretty onerous restriction where most of the instruction set is no longer usable. And in fact, the situation is even worse than this slide makes it seem, because this slide only indicates the opcode bytes, whereas the restrictions are also going to apply to the prefixes and the operands used within the instructions. So given that shellcode is just a program, it's going to have to do a lot of the same computations that any sort of program might perform. You might have to set registers to certain values. You might have to call API functions. You might have to have loops and things like this. So in order to accomplish these tasks within an encoding restriction, you have to choose some machine code bytes that fits within the restriction. So for example, if we want to set the EAX register to the value 0, here's a variety of ways that we might do that. 5 ways, each of them separated with horizontal lines on the screen. So if we're not allowed to use null bytes in our shellcode, for example, then we can use any of the 4 at the bottom that don't have any null bytes in them, whereas we can't use the first one. And if we're not allowed to use the % character, as in format strings, then any of the other encodings will do except for the 4th one, and so on. The last 2 are all printable. Those ones are the ones where it doesn't have any lowercase ASCII letters, and then the bottom one is where all the bytes are alphanumeric. So depending upon the restriction scenario that you're dealing with, it is going to influence how you're going to have to write your program to perform the computations that you want. So the existing solutions tend to work like this. You'll have some existing shellcode that you would like to execute, and it's written in ordinary assembly language without reference to any sort of encoding restriction. So then you'll encode the shellcode in some way, and here we see the bytes have transformed, in this case, to be alphanumeric. And then we'll have to produce some sort of decoder that exists within the encoding restriction and performs decoding of our encoded shellcode. So as for this existing solution, shellcode encoders, the plus side of these methods is that we've studied them quite a bit. We can handle a lot of the common cases automatically, things like no null bytes, no entirely alphanumeric, and so on. And they often work, and they often work quickly. But as for negative aspects of this solution, encoding the shellcode can cause it to expand, and you're going to need extra room for the decoder. When you're actually writing these tools, you're going to have to do a lot of manual work in order to figure out how to implement the decoder within the restrictions. It's not actually guaranteed to work. It's possible that within your encoding there is a way to encode the shellcode, but your tool is not going to find it. And that these things often produce common byte sequences that may be detected by IDS signatures. And that if you look at the code for these things, it's often really nasty and hard to extend and hard to understand what's going on. So now we get to, this is my contribution to this problem. I had to write a shellcode encoder a few years back, and I wasn't very happy with how it turned out. It worked along the lines of what I showed on the previous few slides. And I thought maybe there's a way to look at this problem mathematically and sort of solve every instance of this problem at the same time, and instead of having to write special cases for each individual one. So this is what I came up with. I call my tool Synesthesia. So it can work in a couple of ways. One of them is basically a compiler mode where you tell it essentially what you would like the program to do, the desired functionality, and then the encoding restriction is what the machine code is allowed to look like, and you feed those into Synesthesia, and out comes a program that does what you want and is within the restriction. Synesthesia can work in a couple of other modes as well. You can feed in an existing shellcode and an encoding restriction, and then pass it to the recompiler mode, and it will attempt to determine what your program does and automatically rewrite it in such a way where it fits within the encoding restriction. And then more experimentally, I have an encoder generator mode where you take some existing shellcode and specify the encoding restriction, and then it generates you a decoder that lies within the encoding restriction and also automatically encodes your shellcode to lie within it. My solution has a number of nice theoretical properties, some of which are being elided by the graphic on the bottom of the screen here. So Synesthesia is fully automated. As I mentioned, with the existing encoder-based solution, somebody had to manually analyze the instruction set and figure out how to make things work within a given encoding. On the other hand, my tool doesn't require any sort of manual analysis whatsoever. It handles arbitrary encodings automatically. It's all based on static analysis, so you don't need to actually run any instructions on the processor. So you don't actually need access to a processor of the given variety. It's very flexible. You can specify whatever encoding that you want, and that the idea can also be adapted to any processor that exists. It's exhaustive in that it's guaranteed to find a solution if one exists. And in fact, it can find all possible solutions among those instructions that are modeled by the tool. You can also use it to find the shortest possible solution by number of bytes or number of instructions. And it's metamorphic, so it can potentially produce a different output every time, which means that IDS signatures are going to have a difficult time catching it. And it can even potentially produce self-modifying code. On the other hand, though, so although it has a nice list of properties, this is still a research idea. I find that it works well for short sequences of code, but if you start feeding in things that require 10 instructions or something, it becomes very slow to the point of unworkability. and that there's a limitation with regards to the synthesis of memory instructions at the moment, something that could be remediated, but I didn't do that in time for this presentation. So this is sort of just the beginning of this research. This is breaking the ground, and some more research needs to be done, and better SMT solvers need to come into existence for this to be really practical. So the idea behind synesthesia is based upon a field of study called symbolic program synthesis. And this is the heart of everything that we're going to be talking about for the rest of the program. So I'm going to walk through an example carefully to make sure everybody understands. So program synthesis does exactly what it sounds like. It creates computer programs. You specify what you want the program to do, and a program synthesis tool creates a program for you. So we'll start by talking about synthesis of C-level programs, since it's easier, and we'll make our way down to synthesis of machine language programs. So here's our running example that we're going to use. So the question is, can we create the function x plus 1 by using two statements where each statement has one operator and the operator is either not or neg? So to be clear, the bottom of the slide enumerates all four of the different possibilities that we're discussing. Two not, two neg, and one not. So we enumerated all the possible solutions, and now we're going to encapsulate the way these solutions vary from one another in terms of components. So to be specific, we can see on the first line there's one operator, and then on the second line there's another operator. So we can really represent one of these programs using two Boolean values, where the Boolean dictates whether the first operation is not or whether the first operation is neg, and then the other Boolean value does exactly the same thing, except it refers to the operation taking place on the second line. So these are our components. Components are two Boolean values, bop1 describing the first operation, not or neg, and bop2 describing the second operation, not or neg. So having examined the problem like this, now we can rephrase the question by saying, given this C program here, this C program incorporates our components. It has the two Boolean values, bop1 and bop2. And we have some function f, takes as input an integer x. And then the first line just performs either a neg or a not based on the first component. And the second line just performs, once again, either a neg or a not based on the second component and returns the value. So now the question becomes, is it possible for us to set the values of these Boolean variables in such a way that causes this program to always return x plus 1? So now that we've phrased the question that way, let's just make one more step, which is to phrase the problem mathematically. I'll indicate the connection between the English phrasing of the question and the mathematical phrasing of it. So what we're really asking is, are there values for those two Boolean variables, bop1 and bop2? And the way we write that mathematically is with a symbol called an existential quantifier, the backwards E. So exists bop1, bop2 Boolean values. So are there values for those variables such that for all values of x, and using the keying off the English phrase for all, this corresponds to a different mathematical operator called a universal quantifier. So the mathematical representation says for all x being a 32-bit bit vector. And then in the code, and there's the body of the C function that we were just looking at, and it turns out that the mathematical translation of that is more or less one-to-one with the C. And then we want the output of that function to always be equal to x plus 1. So we're looking for values for those two Boolean variables such that for all inputs, after we execute the function, the return value is always x plus 1. So indeed, this is our formula. I've divided it into 4 components, 4 elements here. Exist components are their values of BOP1 and BOP2 for all inputs, for all 32-bit integers x. And then the program constraint phi program is the body of the C function. And then the functionality constraint, which indicates what the C function has to do, I call it phi functionality. It's just x plus 1. So all of our synthesis formulas throughout this talk are going to look basically like this. So now that we've phrased that question mathematically, as it turns out, there are tools that we can use where we can just pass that whole formula into the tool, and if it can be solved, it will find values of the variables for us that cause the formula to become true. So those tools are called SMT solvers. In fact, only certain SMT solvers will do this. We're using some advanced features. So if we pass this formula off to one of our advanced SMT solvers, it's going to find 2 values for our components that cause our desired behavior. And it is also possible that perhaps a formula we may pass in cannot be satisfied, in which case the solver will return a special value called unsatisfiable. But in this case, the solver has given us back values for the components that cause the behavior that we want. So the values given by the solver are shown off to the right. So here on the left was our original template program. So we're just going to take the value of those 2 Boolean variables and plug them in. And then that is the program that's going to return x plus 1. So if we logical not followed by arithmetic negation is equal to increment of a 32-bit integer. And perhaps you already knew that you could do that, but the interesting thing is not so much the answer to that particular question, but rather the fact that we can ask questions like that and get answers to them, and we'll be exploiting that fact throughout the rest of this presentation. A few more remarks on synthesis formulas before we proceed. As I mentioned previously, each formula in this presentation is going to have roughly the same structure. Specification of the components, a description of the input values, a declaration of the functionality in terms of the components, or of the program in terms of the components, and then the functionality that the program is supposed to have. So if you read the academic literature, you're going to find that these types of formulas are described using a couple of names, which I've indicated on the slide here. Exists for all, one quantifier alternation, effectively propositional, Bernays-Schönfinkel. So just in case you read the literature, these are the words you should be looking for. 2 quick extensions to this basic idea before we move on to synthesizing assembly language programs. So in the previous example that we just gave, we had 2 statements and each had 2 possible operators being used within them. So we used a Boolean value to determine which operator was in use. So obviously if we had more than 2 operators, we would need to use something bigger than a Boolean value. So this slide just demonstrates, here we have, for example, 3 possible unary operations. And so in order to do that, we just use something bigger than a bool, a character, in this case, an 8-bit value. So that's kind of obvious. The next extension is a little less obvious. So we can incorporate unspecified constants into our programs as components, and I'll demonstrate what that means. So this is similar to what we had seen previously, where it has a Boolean choosing between 2 operations. In this case, I've made the operations add or XOR, and the right-hand side of this add and XOR is this constant value called C. Now notice C is also a component. So we haven't specified what the value of C is. So if we wanted to use this template to synthesize the formula, say, not x, when we solve, we're going to need a value for op, and we're also going to need a value for c. So our formula is just going to look like, as one of our components, we're going to use the character c is going to be one of our components, and that's going to be used in the component term, and it's also going to be used in the program term. So then if we feed that to an SMT solver and solve it, it's going to have to provide us with a value for the constant. So in this case, it says, yes, you can synthesize f of x is equal to not x. You just have to set op to false and c to ff, which is all ones. So there's our program that we synthesize, x XOR 0xFF. Okay. Now, let's move on to synthesizing assembly language programs. So, this turns out to be very similar to the synthesis of C programs. In this presentation, we're mostly going to be working with a simple fake assembly language, but make no mistake, this works on real assembly languages too, and in the source code I've released, x86 is amongst the source code that I'm releasing. But if I were to try to talk about x86, there was a lot of complications that go along with it, and I would spend the whole presentation talking about the complications. I wouldn't get to talk about some of the really cool stuff. So that's why I'm using a simple language. So I'm going to define a simple assembly language called, if appropriately enough, simple. And then I'm going to come up with a way to represent it in C. So I'm going to need some sort of data instructor describing simple instructions and a data instructor describing the machine state for a simple processor. And then I'm going to write a little interpreter for my simple language. This is going to consist of a couple simple components. And then, now that we managed to represent our assembly language programs in terms of C, we can just use the techniques that we just saw for synthesizing C programs to synthesize assembly language programs instead. So you keep your bearings straight, here is ultimately where we're going with this part of the presentation. On the left-hand side, I've just duplicated the program synthesis example from the previous section on C, where we synthesize x plus 1 using 2 components. So this is what our formulas are going to look like when we synthesize assembly language programs, that our components are going to be assembly language instruction objects, and then the function is going to take as input a machine state, and it's going to return as output a machine state. And then the individual statements are going to be in terms of the effects of a single assembly language instruction, and that's what we're going to return. So it is ultimately structurally extremely similar. We just have to define this instruction thing, this state thing, and then this function called emulate1, and then we're good to go. So here is the simple assembly language that we're going to be using for most of this presentation. There's no trickery to this. It just has 8 32-bit registers, call them R0 up to R7, and then the instructions are as you see on the slide. They work exactly how you would expect with no tricks. So our language has some binary operators, XOR 2 registers, add or move 1 register into another. Has some unary operators, increment a register, decrement, neg, or not. And then it has some operations that take constant values and add a constant to a register, XOR, and, or. So I'm going to make a little C representation of this language so we can synthesize programs written in this language. So the first thing I do is I just make a little enumeration that describes the possible operands, like XOR, reg, inc-reg, and add reg immediate. Simple. Next, I'm going to make a C structure declaration that describes the content of an instruction. So each instruction is going to have at least an operand and then a left-hand side register number, so something from 0 to 7. And then depending upon the instruction, it may also have a right-hand side register number, and it may also have an immediate 32-bit value. So given that simple has 8 32-bit registers, that the machine state is then just 8 32-bit registers. So we're just going to represent that using an array of 8 32-bit integers. So we'll just use an array, uint32, 8 of them. We'll call that state. So at any given point, our state is just going to consist of the values of the registers at that point in time. So when we're talking about more complex assembly languages like x86, we're also going to need to model things like the flags and memory and so on. So given that all these simple assembly language instructions are going to modify the state, we're going to write a little function called update that modifies a state. So it's very simple. It just takes in some existing state, which register you want to modify, and what the new value of that register is. So for example, if we pass in some existing state, and then we say update register 3 to contain value 0, the new state that we get out is going to look like what we see at the bottom of the slide. And it's going to create a new state as opposed to modifying an existing one. For completeness, I have the code. I'll skip that. If you want to read it, the slides will be online. Almost done. Now we'll just write a simple, this is the interpreter function for a given operation. So you pass in the operation that you want to perform, which corresponds to one of the mnemonics in the simple language, the value of the left-hand register, the value of the right-hand register if applicable, and the value of the immediate value if applicable. And so this function is just a switch. If the operation is XOR reg reg, then it just XORs the 2 register values that were passed in. And if the value is inc reg, it just adds 1 to the left-hand side. And if we add a reg to an immediate, it just adds the left-hand value with the immediate. So this function is very simple. There's nothing complicated about it. And to finish it up, this is the last part of the C representation of simple. Now, this function just performs the emulation of a single instruction. You pass in a state and an instruction, and then it decodes the values of the operands. So gets the left-hand register value, gets the right-hand register value, then calls that function we saw on the last slide with the right arguments, and then returns a new state where we take the value, the result of the operation, and set it into the proper register value. So that's it. So this now is the same slide that we saw previously, but hopefully now it makes sense. So once again, when we were synthesizing C programs, we used Boolean components. And in this example, we had 2 Booleans, and it determined whether the first operation was neg or not, and there were 2 lines like that, and the function took in an integer and returned an integer. So now, given what we've just gone through with representing simple in terms of C, now we can do exactly the same thing with the simple assembly language instructions. So in this case, our components are assembly language instructions. Our synthesis function takes in a state and returns a state, and then the individual lines within the function just correspond to the execution of one instruction. So the first line takes the input state and then modifies it according to the first instruction, and the second one takes that state and then modifies it according to the second instruction and returns the state. All right, so we're basically done. Now we just, in order to synthesize assembly language programs, we're going to need to specify what the functional effects of the program should be. So we're going to have to specify these in terms of machine states. So let's say we want to synthesize a program that increments R 0. So my functionality constraint just says the output value of register 0 is equal to the input value of register 0 plus 1, and then the output value of register 1 is equal to the input value of register 1, i.e. register 1 doesn't change. And register 2 doesn't change, and so on. None of the registers change except the value of R0, which increments by 1. So that's our formula for that. So to be complete about it, this is the mathematical formula that we use to synthesize a simple program that increments R0. 2 components being the instructions, the for all state. The state is a simple machine state. The program is a 2-line program making use of the instruction component. And then the functionality of the program is just it has to increment R0 and leave everything else the way it is. So if we pass that to an SMT solver, it will give us values for the instructions. It will give us values for I1 and I2. So it tells us that we can make a simple program that will increment R0, and the first instruction is add R01, and the second instruction is OR R00, where that is a no-op instruction that does nothing. We specified that we wanted 2 instructions, so it had to find us something for the second instruction. So now another thing we can do is we can ask for different solutions. So we just synthesize some assembly language program, and let's say we aren't happy with that one for some reason, or we just want a different one. So I can just take my existing synthesis formula, what I showed on the previous slide, and then add some terms that say, so give me a solution that satisfies all the constraints I just described, and also either the first operand is not add, or the first operand is not R0, or the second operand is not 1, or the second operand is not or reg immediate, and so on, just stating that something about the solution must be different from the solution we just got. So here I've given the first 8 solutions that I generated by this procedure, where I ask for a solution, it gives me one, and then I solve it again by saying, give me something different than what you just gave me. So here are the first 8 solutions for incrementing R0. Most of them are straightforward and just have a literal increment or add 1 in there, and they have these no-op instructions that I've highlighted in red that have to be there because we specified 2 instructions. But then we can see it rediscovers the trick we saw in the C case, for example. It has not R0 followed by neg R0. And then it also finds it like if I decrement R0 first and then add 2 to it, that's the same thing as adding 1. And if I add some number and then add some other number, where if I add the 2 numbers together, they both add to 1, then that's the same thing as incrementing by 1. And one more quick note before we move on to synthesizing machine language programs. So the formulas we've been talking about so far, they always used a fixed number of statements or instructions. In particular, they were both using either 2 C statements or 2 simple instructions, which is not all that flexible. But what we can do, in fact, is specify a variable number of instructions. This gives, for example, up to 5 instructions. So if I declare 5 individual instructions, then I have another component called num instructions. And then in my synthesis function, it just performs 5 instruction steps. And then based upon the number of instructions, it returns the proper state output. So if I solve a formula like this, it will give me up to 5 instructions, somewhere between 1 and 5 instructions, and it will tell me how many instructions were used in the solutions. So this is a bit more flexible and more general than what we just saw. And we can also revert to the previous behavior by saying, additionally, num instructions must be 2. That just gives us what we just had. Or we could say, I want the solution to have between 2 and 4 instructions, so I add a term to my formula that says 2 is less than or equal to num instructions is less than or equal to 4. All right, let's move on to synthesizing machine language programs. So this is actually very simple. We did almost all of the work just now. There's only one or two steps remaining, a couple of slides in order to synthesize machine language programs. So first thing we're going to do is define a machine code encoding for our language. Our assembly language is called simple. I'll just call the machine code simple MC, meaning simple machine code. Then I'm just going to write a disassembler from that encoding into simple instruction objects, and two functions for that. One function to decode opcodes, the other one to decode whole instructions. And then I'm done, because we just showed in the previous section how we can synthesize simple programs. So if I can just decode machine code bytes and say that they're simple instructions, now I can synthesize machine code programs. So once again, to be clear exactly where we are going with this and what the result is going to look like. So here is our synthesis formula for machine code or for assembly language programs from the previous section. So it had two components, both of which were simple instructions. And then our synthesis function took in a state and returned a state. And it just had 3 lines where it would perform the effects of one instruction, save that, and then perform the effects of another instruction, save that, and return that. So on the other hand, this is what our machine code synthesis formulas are going to look like. Our components are going to be machine code bytes, char MC256. And then our synthesis formula similarly is going to take in a state, and it's going to return a state. And the difference is it's going to decode 2 instructions out of the machine code first, call this function decode to fill in the value of instruction I1 and I2. And then the rest of the function is going to be the same. Once we have our instructions, we just use them to transform the state and return the final value. So all we have to do is write the decode function, and we're home free. So I'm just going to define a very simple machine code encoding for the simple assembly language. This is the first thing that came to mind. No tricks up my sleeve on this one. So for the ones that take 2 registers, I just use the topmost 2 bits to determine what the opcode is. So 0, 0 is XOR, 0, 1 is add, 1, 0 is move, and then the other 2 fields are used for the registers. And then as for the unary operators that only take 1 register, I'll just fix the top 2 bits to 1, 1. And then I'll use the middle field to determine what the operation is. So 0, 0, 0 will be inc, 0, 0, 1 is dec, 0, 1, 0 is neg, 0, 1, 1 is not. And then I'll use the bottommost 3 bits to determine which register I'm using. And finally, that for the instructions that take 32-bit immediate constants, I'll once again just fix the top 2 bits to 1, 1, and then in the reg/op field in the middle, that's going to determine what the operation is. So 1, 0, 0 is going to correspond to add a register by an immediate. 1, 0, 1 is XOR a register by an immediate, and so on for and or. And then the immediate bytes are just going to follow the machine code byte. So that's it. If you didn't follow all those details, don't worry, it doesn't matter. We'll be done with them in 2 slides anyway. I'm just going to write a simple function that decodes the opcode from simple MC machine code bytes, and it just performs the inverse. It looks at the top 2 bits, and if it's not 1, 1, it returns that, and otherwise it takes the middle field and determines what the operation is. And then the decode function is a little more complicated, but don't break your brain trying to figure it all out. It just decodes the opcode as on the previous slide, figures out the length of the instruction, determines the operands, the left-hand register number, right-hand register number, and immediate, and that's it. So that's all we needed to do in order to synthesize machine code programs. Once again, difference between synthesizing assembly programs and machine code programs is, as we see on the slide here. The synthesis of assembly programs used instructions as components, took in states, returned states, and each line would emulate one single instruction. Whereas to synthesize machine code programs, our components are an array of machine code bytes, and then the synthesis function must decode 2 instructions out of the machine code, and then it just finishes up the same way as for the assembly language synthesis. So hopefully that makes sense. So with all that machinery having been built up, now we can do what we set out to do at the very beginning, which is synthesize machine code programs that do whatever we want, where we can also specify restrictions on how they're encoded. So remember that our synthesis formulas look roughly like this. Exist components for all inputs, specification of what the program looks like, and a specification of what the functionality of the program is. So now we're going to add one more term to these formulas, which I'm going to call fee encoding. So additionally to specifying how the program behaves, we also specify how the program is allowed to be encoded. So I'll walk through a simple example here. Let's say that we don't want any null bytes in our shellcode, i.e. no 0 bytes anywhere in our machine code. So we just need to come up with a way to specify this as a formula, and then we can add it to our existing formulas, and now it'll allow us to synthesize null byte free shellcode. So it's just a simple mathematical translation here. For all array indices, called I, so given that our machine code is only 256 bytes length, we can get away with an 8-bit index. For all array indices within our synthesized shellcode, so if I is less than the first instruction's length plus the second instruction's length, then that machine code byte is not 0. So MCI not equals 0. So in total, the formula that we see is the formula at the bottom of the slide. If we add this on to any synthesis formula involving machine code, it's going to give us machine code where none of the bytes are 0. So here is a formalization of all of the examples that I gave in the beginning of the presentation. We just saw the no null byte example. And if we don't want any percentage characters in our shellcode, then we just say none of the bytes are equal to 25 hexadecimal. If we want all the ASCII letters to be uppercase, we just say none of the bytes are lowercase ASCII letters. And if we want all of our bytes to be printable, we just say the byte falls in the range of 21 hex to 7F hex. Or if we want all bytes being alphanumeric, then we say it's either a digit, or it's an uppercase letter, or it's a lowercase letter. So hopefully you can begin to see how flexible and powerful this construction I've shown you is, where we can specify actually anything about the way that our program is allowed to be encoded. So let me give some more complex examples now to get your mind flowing on this. So let's say that I want my shellcode to be such that every byte must be at least as large as the previous byte. So if the first byte is 0, 1, for example, then the second byte must be, it can't be 0, 0, it must be 0, 1 or something bigger than it. So I can specify that by saying each byte is less than or equal to the next byte. Or if it must be strictly increasing, then instead I just use each byte is strictly less than the next byte. Let's say I don't want any repeated bytes in my shellcode, where every byte in my shellcode has to be different from every other byte. Now I just use 2 of these universal quantifiers. I say, so I is somewhere within the machine code, and j is less than I, and then I say the byte at position j is not equal to the byte at position I. Just specifying that no 2 bytes within the shellcode have the same value, and then I can solve that and get shellcode that doesn't have any repeated bytes in it. Or here's a good one, a weird restriction that in theory you could encounter somewhere along the way. Well, let's say my shellcode must alternate between even and odd bytes. The first byte is odd, the second byte is even, the third byte is odd, fourth byte is even, or vice versa, where the first byte is even, second byte is odd, and so on. So I just say, for every index that lies within my shellcode, that if I XOR it with the next byte, and then extract the lowest bit, that it's equal to 1, meaning that the lowest bit of the two consecutive bytes have to be different from one another, i.e. one of them is even and the other one is odd. So I can solve formulas like that. And for example, if I said also that the first byte must be even, then I just say the lowest bit of the first byte is 0. One more crazy example before I show you some real-world solutions that came out of this. You can even do things like, let's say that every word of your shellcode has to be a prime number. Then all we have to do is figure out a way to formalize the concept of something being a prime number, and then add it to our formula and solve it. So for any word in our shellcode, for all 16-bit values, that are between 2 and the word, that if we divide the word by that value, that the result is not equal to 0. That's the same thing as primality. The only thing that divides into a prime number is 1 and the number of itself. So if D is between 2 and the number, then it cannot divide evenly into the word. Okay, so anyway, here's some real-world solutions to some of these constraint problems that I've just described. This one was kind of interesting. So here I'm looking for a solution to set EAX to 0, and I said the first byte of each instruction is less than 20 hexadecimal, and that all bytes are not 0. So the solution it came up with was really clever. It's not something that I think I would have come up with myself, at least certainly not as quickly as it did. It spit this solution out in a couple of seconds. I certainly wouldn't have spent a couple of seconds on this one. So given that we don't know what the value of EAX is beforehand, that once we perform this OR EAX with some large number, and then the SBB instruction is going to subtract, basically, EAX by some other number, and then SBB, EAX, EAX. So if you know x86 assembly language, you know that SBB is like subtract, except it also subtracts the value of the carry flag. So we could use that to set EAX to 0, but we would need to know that the carry flag was 0 before we did SBB, EAX, EAX. So what the first two instructions end up doing is they make sure that EAX is at least the value of this number, and then they subtract some smaller number such that the carry flag is not set as a result of the subtraction, so that on the third line, when we do the SBB, we know that the carry flag is always going to be 0, so that the result is going to be 0 and not -1. Here's some more interesting ones. So let's say I want my shellcode to produce EAX is equal to 1, 2, 3, 4, 5, 6, 7, 8 hex, and I say the bytes have to alternate between even and odd. And then, in fact, if we look at the solution, we could see first byte is even, second one is odd, first is even, second is odd, and so on. So it moves some large value into EAX and then sort of like surgically ands off the proper bits to get rid of the other ones, and it does that by interleaving, setting the top byte to something odd, and then on the next step, anding it with something even. And that if I specify that not only do the bytes have to alternate even and odd, but the first byte has to be odd, that it has to sort of do some more trickery in order to make that happen. Okay, so the takeaway from this is that the construction I just described is compatible with absolutely any encoding restriction that you can specify as a first-order formula. So as long as we know what the encoding restriction is, then we just specify it, and we can see later, if I have time, that we can automatically determine what the encoding restriction is. So if we already have some some machine code that does what we want, but it doesn't satisfy the encoding restrictions, we can simply use the functionality of the existing program as the functionality constraint and synthesize a new program. So I'll show that with graphics. If this is my existing program that does what I want, and then I assemble it into machine code, so then I can just take its, represent what impact it has on the machine state, and then use that as my functionality constraint to synthesize a new program, where here is my synthesis of the machine language program, and then I say, the effect of the machine language program must be such that it has the same effect on the output of the EAX register as the other program, and it has the same effect on the output of the ECX register as the other program, and so on. So just automatically derive a functionality constraint, and then use that to synthesize a new program. I think this is the last extension I will have time for, which is a shame because I spent a long time on the decoder synthesis thing, but it'll be in the slides. So let's say that we want to find the shortest program that satisfies some given set of restrictions. So to simplify a bit, let's just call a program good. We'll call components good if they satisfy the functional and encoding constraints. So now we just want to know what is the shortest good program. So mathematically, we'll say, is there a best program, exists best, such that best is good, and for all other components, if the other components also satisfy the encoding restrictions and the functional restrictions, that the length of the best program is less than or equal to the length of the other program. So we're quantifying over all other solutions and say, find me the solution that has the shortest, that has the minimal length amongst them. So for example, here's the shortest solution to the increment constraint, incrementing R0. It has some no-op and an increment, and both instructions are 1 byte, so it's just 2 bytes in length. And I could also flip it around and say, give me a solution such that the best program has length greater than or equal to any of the other solutions. And then it's going to find me 2 instructions that are 5 bytes apiece, so the result is going to be 10 bytes in length. So I think I basically have to just move to the conclusion at this point. It's a shame I have cool stuff about how do you synthesize loops for decoders automatically and so on, but I simply don't have time. Okay, so as for the limitations, so same problem that you encounter when you're using an SMT solver for absolutely anything, which is that sometimes the constraints happen to be easy to solve, and sometimes they happen to be difficult to solve, and it's kind of difficult to predict ahead of time whether it's going to be simple or not. So for this example here, you know, if I wanted to synthesize machine code based on the value of this output buffer, which is returned from this function crypto hash, so now I'm going to have to invert crypto hash in order to solve in terms of my input. So that's the second pre-image problem, and that's not going to happen. You're not going to be able to solve those constraints. Same problems that automated exploit generation has. A more serious problem, and this is ultimately the reason why I wasn't able to get memory support working. So when we have our quantifiers, like the backwards E exists and the upside down A for all, we cannot actually use arrays inside of those quantifiers. So for synthesizing machine code, it turns out to be pretty easy. I just instead use bytes, exists machine code byte 0, exists machine code byte 1, and so on. And then I just have a little function that returns me the proper value of the proper byte. So this is not a problem, actually. Instead of synthesizing a 256-byte array, I can just synthesize 256 individual bytes, and this presents me no problem whatsoever. But on the other hand, when it comes to using an array as part of the state, this is a less surmountable problem with the current technology. So given that we cannot use an array as part of the state, well, with an SMT solver, you tend to use arrays to represent memory. It's not a big deal for representing registers or flags, but for memory, it is a problem. So if you can't use arrays in your state, that means you can't represent memory in your state. However, this is not actually a theoretical problem. In theory, you can solve these constraints, so this is actually just an issue with the current implementation of YISIS that I'm using. I didn't check to see whether Z3 or CVC4 would allow me to do this. I didn't have time, but it's possible that I'm getting some indication from the audience that Z3 will let you quantify over arrays, so thanks, audience member. So as for theoretical limitations, these are things that you cannot solve. These will be there forever. You can only synthesize up to a certain number of instructions, or as I showed, you can synthesize up to 5, for example, instructions. You can't synthesize, give me a program of any length. You have to specify the maximum length. And that these other limitations relate to the loop and decoding work, so I'm not going to talk about them since we didn't talk about them in the presentation. So at present, here's what works and what doesn't. We can do straight line code for simple MC and x86. Synthesize equivalent snippets for simple MC and x86, find the shortest solutions for both. Decoder synthesis works in simple MC because I hacked it up in order to add fake memory access instructions. But it didn't work in x86 because I didn't want to hack it up and add fake instructions. That's just ridiculous. I didn't talk about input preconditions, but that works on both. And then memory operations don't work. And there's no integration with exploit generation, which is something else I talked about but didn't get to. So here's some performance evaluation of how this works. It's really fast for simple, for non-complicated, trivial sort of functionality. If we need to, do something like set a register to a value or take like the absolute value of some register and figure out how to implement that functionality or something. You can generally do that pretty quickly. As you can see, most of them are between like 0 and 6 seconds. When we start synthesizing decoders, that becomes very time consuming. And I wish I'd actually put some more examples on this slide in that when we start to synthesize things that are like 6 instructions or more, or the functionality that we're synthesizing is very complicated, or the encoding restrictions we're using are very complicated, then it tends to be the case that the solver runs forever and doesn't stop. I wish I had indicated that on this slide, so just keep that in mind. It's not all rosy. Don't expect all your formulas are going to solve in 6 seconds or less. That is definitely not the case. That's why more work needs to be done. So in the future, I'm going to look into maybe stochastic super optimization for this, which is a technique based on genetic algorithms for doing program synthesis. Perhaps we could represent the input restrictions as being some sort of grammar and have a generative model to come up with mutations. And then I'm going to look into ways to make the existing stuff faster. As I said, YISIS will time out on complex formulas, so do some profiling to see if there are any obvious bottlenecks that I can get rid of. And then their specific solver has something called an implicant generalization heuristic, and I want to see if I can do something special for this problem for that. And that maybe there is some benefit to be obtained by making a custom SMT theory that describes an assembly language. Who knows? Truthfully, I'm sick of working on this problem, so I probably won't do any of this. But if anybody wants to pick up where I left off, this is where I'd start. OK, so I need to clean up the source code before I release it. It has not yet been released, but I did write all this code, and it all works. So just want to make sure everything is clean and consistent. The source code is in terms of YISIS Lisp. So the stuff for simple MC is, their scripts are about 1,000 lines apiece, and then for x86 it's more like 3,500 lines of YISIS Lisp or something like that. So I'll announce the URL on my Twitter account, or just look in the standard places. I run the reverse engineering Reddit and stuff like that. So you'll find it if you care. Yeah, I'm done. Okay, so last thing. In case you're interested in SMT-based binary analysis research and you thought that I did a decent job of presenting about it, in fact, I made a training course that's a week long that covers this stuff in great detail, doesn't really assume you know anything about math or like academic computer science, and just starts from the beginning and ends up developing an entire framework for using it for solving reverse engineering problems. So if that's interesting to you, there's some public courses available, and I'm also available for private classes. Do your part, keep computer security weird. So that's it. First presentation I'm aware of on synthesizing machine code programs, period, let alone with encoding restrictions. There's still work that needs to be done. Works decently well for small and simple examples, but more stuff needs to be done for scalability, and the source code will be released in case you want to play with it. So that's it. If anybody has any questions, I may have. What's up?
Hola. Me lo hace a propósito, perdón. Bueno, nos quedamos sin tiempo real porque ahora para la otra charla, Rolf is gonna do the questions.
Oh, sure. Okay, meet me in the other room if you have questions.
Spanish, English, todo al mismo tiempo. Mi cabeza nada más, chicos. Bueno, very good. Y un fuerte aplauso, por favor, chicos. Gracias.